Okay, Professor Pega had a presentation about FGB Reversible, so how he wants to return vapor from the microchannels to the bypass, and Mr. Pashai has a nice presentation about heat pumps, and my presentation will be concerned how we want to implement FGB into the heat pump modes in automobile air conditioning. So here is some background about my presentation. Everybody should know that microchannel evaporators are nowadays widely used in MEC systems, in mobile air conditioning systems, and increasingly also in stationary AC systems. One of the main issues for microchannels are that we do not have that good distribution of two-phase refrigerant in the headers. Some of the possible solutions can be geometry remedies, like baffles, flow constraints, and something like that, or generate mist droplets at the inlet of the evaporator header, or flash gas bypass. On the left side, you can see one of the typical microchannel evaporators, which is used in MEC systems, and on the right side, you can see the infrared image of that microchannel when it's running. So what we can see here, that at the inlet header, at the first part, we had at the bottom liquid, and on the top we have a vapor, which is going to those first microchannels. And actually, since we have a vapor going into those first microchannels, we are sacrificing this surface, and we do not have any heat transfer on that surface. And later, liquid is filling up the header, so liquid is going through other microchannels, so where we have a better distribution. What is actually flash gas bypass? That's a concept used in industrial systems for many years ago. It separates and bypasses flash gas, and we feed liquid only to microchannel heat exchangers. Professor Hrnjak proposed modifications for MC systems together with Beaver, then with Elbel and Milošević and Tuo in those years. And primary benefits of FGB is to improve refrigerant distribution in microchannel heat exchangers, to get a lower pressure drop on refrigerant side, and to get better effect on a heat transfer. Here you can see the typical drawing how system works in DX mode, and then how we improve it with FGB mode. We have here compressor, then we are going to microchannel condenser, then through internal heat exchanger, through expansion valve, and in DX mode we go directly to the microchannel evaporator, but with the FGB, instead of going directly to microchannel heat exchanger, we are going to this flash gas tank when we have a separation between liquid and vapor, and then later we bypass that vapor through internal heat exchanger to the compressor suction. Here is one example where we demonstrated how FGB is better than DX in the same system, automotive system. We used original parts from Toyota Camry 2007, but we had to modify evaporator because when you use FGB system, it requires to use single pass design to preserve initial distribution, because after each pass you generate more and more vapor, and then you again have the two-phase flow through your microchannel. So basically we had two chambers, environmental chambers. One was outdoor, where we put condenser. One was indoor chamber, when we had the evaporator. We had a compressor, and also we had the first DX mode, and then we add this flash gas tank to the same system to see what is the difference between those two, and do we have some improvements or not. So here is the evaporator modification, because we had the troubles to make the same evaporators. To modify the same original Denso evaporator to single pass, we used more or less similar evaporator, and we made it to the single pass and single slab, and we also added transparent headers on inlet and outlet. And here you can see the test conditions. It was 35 degrees on inlet, indoor and outdoor, and here you can see some dimensions of the evaporator, and you can see that air side area here was a little bit lower than original Denso evaporator. So when we got the results, here you can see with a dashed blue line and solid light blue line, comparison between capacities in FGB mode and in DX mode, and you can see that we increased the capacity for approximately 16% up to 70%. And also here you can see with the dashed red line and solid violet line, comparison between COP in FGB and DX mode, and it was average 10% higher in FGB mode. And why is that? When we took infrared images, you can clearly see that we sacrificed more surface in a DX mode on our evaporators due to a low distribution flow of two-phase refrigerant, and in FGB mode you can see that only at the exit in the right upper corner we had a superheat. So we had a less unsatisfied surface on those evaporator in FGB mode. Okay, we were trying to match then we were trying to keep the same capacity in both modes, in FGB and DX mode, and when we were doing that, we noticed that DX system compressor was running at 900 RPMs, and in FGB mode, compressor was running only at around 500 RPMs. And also later and later, you can see that in different conditions of compressor inlet superheat, we were running DX in 1600 RPMs, while in FGB mode we were running compressor only on 700 RPMs. And why is that? Also because of the better distribution over the microchannel heat exchanger. And here are some pH diagrams where you can see the comparison between FGB and DX, where we had a higher evaporation temperature for 3.5 degrees. We had a lower pressure drop over the evaporator. Also, compressor inlet pressure was higher in FGB for 31 kPa. And when we were matching capacity and take pH diagram, also you can see here that our temperature of evaporation was higher for 7.8 degrees in FGB mode, that we had a higher also pressure drop over the evaporator, and our compressor inlet pressure was higher in FGB mode for up to 140 kPa, and also condensation pressure was lower for 140 kPa, and that shows us that COP was way higher in FGB than in DX. You can see here that FGB COP was 2.8 and in DX was only 1.53. Also, evaporator effectiveness was increased when we were using FGB separator, and you can clearly see that here that FGB evaporator effectiveness was higher than in DX at a compressor speed of 900 RPMs, and evaporator effectiveness was calculated when you divide your calculated capacity with the maximum capacity theoretically. Also, distribution factor was found by Professor Hrnjak, Bovers and Bujak, and what is actually that factor? That's when you calculate the height of the borders between your superheated area and the area where you still have a liquid. So when you calculate it with this factor, you can see here also that our distribution factor was way better in FGB mode than in DX mode at a compressor speed of 900 RPMs. So here are some interim conclusions. System COP and capacity significantly improved by FGB because of more uniform distribution. We had a lower pressure drop over refrigerant on the refrigerant side through our evaporator, and our evaporator has a better performance in FGB than in DX, so because of higher effectiveness and low pressure drop. But since we had a smaller evaporator, we have to be honest, we used smaller evaporator, and that amplified positive effects on FGB, and that's shown on this diagram right here. But distributor could have improved performance in DX mode. So now is the question, because we have a better performance in AC mode, can we use this FGB in a heat pump mode in a reversible system, and how to control it? Okay, the answer is that FGB can easily work in reversible mode. For conventional reversible system, 4-way valves are used. For FGB, a 4-way valve should be modified, and FGB can use internal heat exchanger and only one expansion valve, while conventional needs two. And here is some graph of our prototype, how we want to implement 4-way valve into our system. So here we have a compressor in AC mode going to outdoor heat exchanger, actually to the condenser. From the condenser we are going through this 4-way valve, which can rotate and switch from AC to heat pump mode, going to internal heat exchanger, then to this flash gas receiver. Then we feed liquid only to the indoor heat exchanger, which is evaporator, and then from evaporator again through internal heat exchanger to the compressor inlet. And here is just the opposite when you switch when you actually rotate this 4-way valve. Okay, here is the prototype of FGB reversible system what we are making, actually what we made. Here you have a condenser, evaporator, compressor. From compressor In AC mode, we are going through those ducts, through those pipes, sorry, to this four ball valves, where we are switching from one mode to another, and on the bottom we have another ball valves where we are switching so far manually one mode to another. And in the future we want to change those 8 ball valves to one 4 valve, which can replace all those 8. This is the system what we made in our laboratory. Here you can see the compressor, condenser, evaporator, and here is the FGB receiver. So evaporator was bare 6-pass evaporator, which we modified to 1-pass evaporator because FGB requires single pass. Condenser was 3-pass condenser with 33 tubes, Denso compressor of 90 cubic centimeters, and FGB separator. So what we are actually doing and what is actually FGB, you can see here on this graph. From expansion valve you have a total mass flow which is going to this FGB separator. Then you have a vapor which is going with quality multiplied by total mass flow through the bypass valve, which is going to internal heat exchanger and then to the suction line of the compressor. And from here you're feeding up only liquid to evaporator with a total mass flow of 1 minus quality multiplied MR, total mass flow. And here sometimes we can see the swirl which can suck the vapor to the inlet of the evaporator, and we can easily avoid that with putting just a little bit cross on the bottom. And with this design we had to do this, and later we are going to change maybe this design and to optimize it to the optimized conditions for both modes. Okay, like Pega said, we are visualization this system. We put 2 webcams. One is recording the evaporator outlet, which you can see here. So we are actually leaving a little bit of, maybe you can see, maybe not, I don't know, but some of the liquid is going out from the evaporator. Here is the evaporator outlet, and some of the liquid is coming out from the evaporator because we don't want to have any superheat in our microchannel heat exchanger. And then that liquid goes to internal heat exchanger, when after that goes to compressor suction. And the second video is that we are recording the separator, and we take a look how it behaves in a different regimes. Is it going up and down? Because we noticed that different level change the separation in this FGB separator. So actually how we control those 2 valves. Right now we have 2 valves which we are controlling. They are electronic step control valves. One is expansion valve, second is bypass valve. And we installed 2 PID controls in our LabVIEW software. So at this point we want to control subcooling and superheated compressor suction constant at, at this point we want to control subcooling, yes, and superheated compressor suction constant at 10. Okay. And later we want to maximize COP controlling subcooling and superheat. So parameters for PID parameters for subcooling controls was 0.3, 0 and 0.1, and for superheat control was 0.1 for CDS2 and 0.05 for CDS4. Actually we were trying to find the best bypass valve and later maybe to change it with some orifice, because nobody wants to spend such money on those valves if we can use only orifice, which can reduce cost of our system. So here are some effects of our bypass valve size when we were using CDS2 and CDS4, which was larger. And in those regimes, when we were keeping compressor speed of around 900 RPMs, temperature was 30 degrees on condenser, and on the evaporator was 27. When we were controlling expansion valve and the bypass valve opening, I don't know why here is not dashed. Okay, never mind. This solid line on the top is representing the CDS2 opening, and you can see at some point we had to open that valve up to 100%, which is not good. And even in that condition, we couldn't reach the superheat to 10, so it was around 6 or 7. So that means that we have a higher restriction of CDS2. We had to change it to a CDS4. So here you can see the opening of, with a green solid line, you can see the opening of CDS4 valve. So we open it up around 40% or 50, and we could we could control the superheat at 10 degrees. So, because we also noticed that our expansion valve is well selected, and we could control our subcooling with our expansion valve, because you can see with the bottom red line it was opening of our expansion valve, and the red line is showing subcooling on condenser outlet, so we could manage it that our subcooling was at 10 degrees. So we didn't change anything about our expansion valve. So when we change this bypass valves to CDS4, which is bigger, we start running some test conditions from our test metrics in I30A condition and I30 condition, which we change actually right now the only temperature on the condenser inlet. So we are modifying the temperature in our chambers so far only. So here are some results when we compare those two conditions, and I have to be honest, those results doesn't show that much, because they are showing only that we can run this system and we can collect the data, and so far we didn't get a green light to publish all our results in a heat pump mode, in AC mode. So I'm just showing now the results at the very beginning of our measurement. So we could control the air temperature of the condenser, inlet and outlet. We could control air temperature of evaporator also in inlet and outlet in conditions of 38 and 30. Also, we could manage control of subcooling of condenser outlet, superheat of compressor inlet and evaporator outlet, and we could do that without any problems. So, and also, like I said, in different conditions we had a more or less different level of our liquid in our separator. So you can see in our condition of 38, our level of liquid was a little bit above the inlet of the two-phase flow. So when you have a two-phase flow inlet right here to the liquid, we didn't have good separation here. So vapor was going down, I think, yes. And here are the comparison between capacities and compressor work in those two regimes, and we could manage it very well so far. We had more or less similar capacities and compressor work in those two conditions, and we could also control COP. So, at the end, I would like to have some conclusions that we demonstrated earlier that FGB can improve performance, capacity and efficiency by reducing pressure drop and improving distribution. Then transients are manageable and startups are presented with selected characteristics of PID controller. Analysis of startups indicates good sizes of bypass and expansion valves, and later we would like to implement that orifice if it's possible. And also we are working now on performance maximizing control strategies, and I really hope that next year we can publish real results from the heat pump mode and AC mode. Thank you for your attention. And